of solving the VIP's problem. Equation one. Equation one is the that we are dealing with, which describe the VIP problem. Then we have so many people that have worked on this problem before, solving something like this. That is what we have in equation 2, 3, 4, 5. In equation 2, equation 2 was talking about extra gradient method. Introduced in 1976, is a common type of is the most common method used to solve a VIP. And we have the modification in equation 3. Then okay, in equation 3, then also in equation 4, we are due to some drawback in that equation 3, Sensor et al. Introduce another subgradient method. Then another algorithm by subgradient extra
Mr. Akajola, ẹ jọ̀ọ́ ẹ mú ti ara yín, ohùn yín jáde síbí báyìí.
Kò ṣe fọ́ọ̀sì mi sọ̀rọ̀ pé.
Okay, ọ̀gá Dr. Alukemo Sosa.
Yeah, so equation 4 is talking about it's an improved method that try to solve the drawback in that equation 3. Then also we have another one proposed by which proposed his own iteration TEGM, and that algorithm use one projection to solve each iteration. Then in section 2, I'm trying to use that paper again. In section 2, it's just some background work. Then in section 3 is the main result in section 3, which is algorithm 3.1, and lemma 3.4 is used to establish the boundedness of the sequence Xn. Then in section 4, we have series of numerical simulations, to describe how the newly introduced algorithm work, and we can see from the result that I think it worked better. It converged faster than the other, considering the time. So I think that is that is all in the paper.
Okay, well, that's a summary of the paper. But then you jumped to algorithm, and if you don't mind, I would like you to take us through that, because I'm asking you to review means where the major thing is the chapter 1, because that's the motivation for the new study. And they don't just jump into the motivation. They have already mentioned what has occurred in the literature. So you jumped 2 methods that were introduced. So you may want to see those methods and try to compare them with what you have started with. For instance, just like I mentioned, 2 and 3, there's no difference between 2 and 3. The only thing is that an extra step has been introduced to 2 to have 3. So if you look at 2, it's just the extra gradient method with 2 projections, 2 evaluation of the operator A. And if you come to 3, it's the same thing, 2 projection and 2 evaluation of the operator A. But in the third step there's another problem there. And you can see that from this definition here. They say where A is the monotone operator on C and N is continuous. That's the property of A. While F is a Lipschitz continuous and strongly monotone operator. So this is solving another different problem entirely. This is not the VIP. So this problem, they call this bi-level VIP. So we see that separately. So, but they have just mentioned it because it also includes the extra gradient part there. So that's why this has been mentioned. So 3 is just using the extra gradient method to solve a different problem entirely. So the problem being solved there generalizes the VIP that is being considered in this paper. They shouldn't have added it, but since they've added it, I have to just clear that. So this is not entirely for VIP. This is for bi-level VIP because of it solves one VIP here and another VIP here. So, but what you said here is rightly correct. So this is a subgradient extra gradient. So it's a projection and another projection onto our half space. So that has to be mentioned that this TN here is an half space and is defined here. That's what you see in the middle here. So a half space, and this is the Senk extra gradient method, which you can also see as a forward, backward, forward method. You can also see it as forward, backward, forward. They call it forward, backward. So this is forward, this is backward, and this here is forward again. So we call it forward, backward method. So saying extra gradient is also called forward, backward, forward. So this is what I said on points. So these are other things that you should have mentioned here. And then now there are some things that you probably didn't mention as well here. This step length here, this lambda controls this operator A. The lambda that you're seeing associated here controls the operator A. So it's there, here, it's lambda here. In the extra gradient method that was given here by Koplevich by 2, it's just a constant. You see lambda. But how is that lambda selected? The lambda is selected in this open interval, 0 and the reciprocal of the Lipschitz constant of the operator. So if you come to the next one, here it's also it's a sequence. If you look at 3, method 3, it's a sequence, right? And also
Yes.
it's selected the same way that other one is selected. So selected in the open interval 0 and then 1 over L. And finally, what else? The same thing here. This is also a constant, right? Also selected in the same interval. And if you come to the Senk extra gradient method, the step length as well, which controls the associated operator A, is also dependent on the fact that you are seeing it that it includes 0, the interval includes 0, and this, so we say it is dependent on the Lipschitz constant of the operator A. So that's why you see here that they say another shortcoming of algorithms 2, 3, 4, and 5 is the choice on step size. You see, so that choice being selected in this interval means the execution of the method depends on knowing the Lipschitz condition of the operator. And most times there are some nonlinear equations that not even those ones are modeled in real life situations that if they give you, you might not be able to find the Lipschitz constant. So it occurs like that. So what do you do? So that's one of the essence of what they've done in this paper, to introduce a step size which does not depend on the condition of the operator. So, and that's why you see this update, lambda n plus 1 here. That's what calculates that step length. So what I'm saying in essence is that you have not taken us through algorithm 1.1 and algorithm 1.2 before going to preliminary. So maybe I leave somebody. Yeah, we thank you for the presentation and ask somebody else to take over from there.
Okay. Yeah, can I go next? Should I go next?
Yes, you can. Yeah.
Yeah. Based on what Dr. Aluko said and what you've just added as well. So in paper and Dalilodi, only one low 2 initial type algorithm. Sorry, am I permitted to speak Yoruba since we are all Yoruba here?
Yes, you can go ahead.
I think it will. Yeah, okay, so 2 initial type algorithm to solve the variational inequality problem. And I want 2 initial type algorithm here now ni Schenck extra gradient method àti Modavi viscosity scheme. So wọ́n introduce the level àwọn method yìí láti fi.
Do you want to share the screen? You want to share your own screen?
Ẹ̀ka máa tí n bá ti require rẹ̀ máa jẹ́ kẹ́ ẹ gbọ́.
Oh, you want me to feel it back?
She feel it for now, bye.
Okay.
So wọ́n create new method yẹn láti fi yanjú àwọn àbùjẹ̀ǹjẹ̀kù eléyìí tó wà nínú àwọn existing algorithm. Alákọ̀ọ́kọ́ náà àwọn existing algorithm yẹn ni extra gradient method. So wọ́n ṣàlàyé pé extra gradient method yẹn wọ́n ti kọ́kọ́ máa ń lò initially láti fi solve saddle point problem, then lẹ́yìn náà wọ́n fi solve VIP. So condition tóun náà ni pé operator A wá ń bẹ̀ yóò máa wà monotone, yóò dẹ̀ máa wà Lipschitz continuum. So wọ́n lò ní Euclidean space àti Hilbert space. So tá bá lo extra gradient method yìí láti fi solve VIP, a máa ní weakly convergence. Nígbà mìíràn lẹ́yìn a lè bùkátà bóyá láti wò bóyá wà strongly convergence or not. So Meigyi òun propose another method tí a mọ̀ sí subgradient extra gradient method. So fóun bẹ́ẹ̀ a ní operator méjì A àti F. So A yẹn náà yóò máa wà monotone, yóò dẹ̀ máa wà Lipschitz continuous, but F òun máa wà strongly monotone àti Lipschitz continuous. So solution set yìí tóun òun máa wà strongly convergence. Gẹ́gẹ́ bá ṣe mọ̀ pé tá bá ní projection kankan lọ́tọ̀ fún alára rẹ̀, ó mọ́ nira láti wá ambọ̀nsibọ́sí tá bá ní projection méjì. So torí tá bá ní projection méjì yẹn òun ló le láti wá, kódà tí ó bá le gan náà a máa ní lower efficiency. So tàbí ká application interview mọ́ lo kó mọ̀ dá. So that's why ní sensor ló fi replace second operator yẹn pẹ̀lú tí a mọ̀ sí constructive half space. So but Senghi tí òun tún improve tí sensor ti ṣe further. So a ní just one, òun kàn lo one projection níbẹ̀. So in tí method táwọn wá lò nínú paper yẹn ni pé shortcoming tó wà nínú àwọn method mẹ́rẹ̀ẹ̀rin tá ti dákọ̀ yìí, extra gradient method ni o, subgradient extra gradient method ni o, irú eléyìí tí sensor lò tó replace operator kejì pẹ̀lú half constructive half space àti ti Cheng extra gradient method yẹn. So shortcoming tó wà ń bẹ náà ni pé tá bá fẹ́ mú step size, so a dẹ̀ ti mọ̀ pé step size ó ṣe pàtàkì láti fi prove convergence wa. Àwọn step size yìí ó dẹ̀ mọ́ depend lórí àwọn Lipschitz constant wa. So gbàtà ti mọ̀ pé àwọn kíní ó wà important, early náà ó dẹ̀ wà important. Nígbà mìíràn early ó mọ́ ń ṣòro láti wá tàbí ká tiẹ̀ mọ́ mọ̀ rárá. Ìgbà míì tá bá mọ̀ early gan gbó yẹ pé early yẹn yóò mọ̀ wà nínú value early yẹn náà, interval yóò mọ̀ wà between 0 and reciprocal of L. So early yẹn náà ìgbà tó jẹ́ pé tó kéré náà ni, so a máa yóò mọ̀ slow down convergence rate wa. So ó mean pé a require larger step size. So that's why ni wọ́n fi propose two methods yẹn. So ti Senghi extra gradient method yẹn including kí la ń pè Modavi viscosity scheme. So náà ni new problem tó ṣe ń bẹ. So wọ́n dẹ̀ prove convergence yẹn. So a yọ P kúrò nínú scheme wa, èyí tó jẹ́ Z yẹn. So wọ́n dẹ̀ apply àwọn triangular inequalities àti wọ́n kọ́ square láti lo perfect square láti fi square each of them. So wọ́n dẹ̀ break lọ́tọ̀lọ́tọ̀. So ìgbà tí wọ́n show pé it's less or equal to constant. So ó show pé ó wà bounded. So ẹ̀dẹ̀ sọ fún wa pé the same way náà ló jẹ́ pé pé the other time tẹ́ ṣe ní the other class ẹ proof boundedness fún ìkànnà àwọn method yẹn fún wa. Ó dàbí kí ni ti APAN. Ẹ sọ fún wa pé gbogbo method tí wọ́n bá ti lo APAN fún the same approach yẹn náà la máa lò. Òun náà ni pé tá bá ti lo scheme yẹn tá yọ P kúrò ńbẹ̀, a dẹ̀ lo metric projection láti fi split rẹ̀ ká tó lo bóyá bí àwọn other inequalities àtàwọn kíní yẹn. So tá fi prove kílókù ẹ̀ náà. So gẹ́gẹ́ bẹ́ẹ̀ náà ni fún Senghi kíní yìí náà. So tá bá ti yọ kúrò nínú P, so tá dẹ̀ apply àwọn inequalities yẹn sí. So tá bá ti rí ẹni problem ta fixed point problem ta fẹ́ solve tán dẹ̀ lo Senghi yìí náà fún àti àwọn kílókù ẹ̀ náà the same approach náà la lò láfi prove it. So addition tí mi fẹ́ fi sí nìyẹn.
Okay, so anybody that's going to go next should correct whatever they think is the anomalies of his presentation. So whoever is going next should take over. And if you want to share your own screen, you can let me know. Kajola, present. You have not presented. Is it there?
Muted.
Oh,
But
hello. Let me share my screen, sir.
Okay.
So, láfikún pẹ̀lú nǹkan tí wọ́n sọ. Interface tí pépà ìdálé lórí ni tools of modify initial Seng extragradient method láti solve monotone operational inequality problem. So in this paper, so they were proposed to solve the operational inequality problem with monotone and elliptic continuous mapping in Hilbert spaces. So the fourth algorithm, so let me just move to the algorithm they use. So the fourth algorithm here need the computation of only the one projection onto feasible set C per iteration. So here in this algorithm, so they use double inertia here. So they use double inertia. Okay. So we have our inertia times here. So we have Wn equals to xn plus alpha n this here on the screen. So and we have projection yn to be PC of this. So then when yn is equal to wn, then we stop. But if yn is not equal to wn, then we proceed to the step 2. Then we compute the xn plus 1. So which is the viscosity that we have here. So and here we have our Seng algorithm here, set n. So this is our Seng algorithm here. Seng. So here we have n equals to n plus 1. If n equals to n plus 1, set n equals to n plus 1. And if you don't get what we are looking for, then we go back to the step 1. So and here we have some preliminaries and the result of the other authors that's applicable. So yeah, in our main result here. So here we have okay. So here we have our step length. We have letter n to be minimum of. So we have already explained the lambda before, so we don't need to talk about that now. So here we want to prove the convergence. So we want to prove that P is in solution set of relational inequality C, A. Then the definition of set n is used in lemma 2.2. So here we have ym minus lambda n into a of ym minus wn. So here we introduce the triangular inequality that norm of a minus b give you norm of a square plus norm of b square minus 2 into inner product a minus b. Yeah. So yeah, what we need to expand this using the inequality triangular inequality. So here we have we brought this negative p here, so we have y minus p. So by using this, so then we have this one is y minus p. So this norm of a, that will be a, and then this one will be b. So that's how we open this and solve all these ones. So we prove the first thing we need to show here is so the convergence so the boundedness of this iterative algorithm. So after showing the boundedness, then we solve for the solution set of relational inequality problem. So we solve for the solution set, then we are going to show that our p bar, I don't know what they use here. So we have to show that the solution set is in is weakly converges to P bar. Let me see. So we have to show that the solution is weakly converges to P bar to show the weakly convergence. Okay. So here they use S star. So S star is in solution set. So we should show that it's weakly converges. So after this, then we solve the strongly convergence. So what briefly what I was saying about this paper is that the two algorithms proposed are proved to be proved to have the strongly convergence results. So which is the better than weakly convergence. So and we have a numerical example that was used to back the two iterative algorithm up to show the efficiency of the algorithms. So that's all, sir.
Are you done?
Yes, sir.
Okay, let's have Dr. Lorna. I'm going to make a general comments after Dr. Lorna's presentation. Lorna, are you there?
Ẹ ṣí kíní microphone.
I'm muted.
Yes, sir.
Bàbá tó ń lọ Nàìjà.
Ọ̀gá mi. Ìmọ̀ pé iná ti múra.
Ọmọ òtútù tó mú ilé yá. Ọmọ Nàìjíríà ẹ ṣe.
Ṣé ká lọ?
Bàbá ti lówó. Ìsáyè tẹ̀ sínú báàgì.
Ẹ lè dùn mẹ́rù.
Ẹ jẹ́ ṣe àti rí screen ni, sir.
Yeah.
Bẹ́ẹ̀ni.
Láti máa gba àkókò wa, so pẹ̀lú explanation táwọn èèyàn mi ti ṣe síwájú. So a ti sọ̀rọ̀ nípa àwọn problems pẹ̀lú from the láti be two modification of the initial term. So tí wọ́n fi develop iṣẹ́ yìí. So láti bí àkọ́kọ́ wọ́n ti define the first equation as a operational inequality problem. So níbi ẹlẹ́ẹ̀kejì yẹn a rí i pé a rí Picard iteration léyìí tó jẹ́ PC into xn minus lambda axn. So ìgbà tí wọ́n ṣe iṣẹ́ yẹn a rí i pé ìgbà tí wọ́n ṣiṣẹ́ yẹn wọ́n ti ṣàlàyé fún wa pé nínú àwọn method tí wọ́n ń lò láti fi solve operational inequality problem òun náà ni extra gradient method. So ìgbà tí wọ́n lo extra gradient method àbújẹ́kùn ẹ̀ òun ni wọ́n try láti develop tí wọ́n fi introduce àwọn oní PC méjì yìí so níbi equation 3. So hello.
Yes.
So òun ni wọ́n try láti develop. So wọ́n develop àwọn iṣẹ́ yẹn bọ̀ láti ẹ̀yìn wá títí tí a fi débi the last equation which is this equation 5. So tí wọ́n ti sọ̀rọ̀ seng àti àwọn iṣẹ́ tó ṣe níbẹ̀. So gbogbo àwọn problems yẹn, àwọn àbùjẹkù tó wà níbi àwọn iṣẹ́ yẹn ni wọ́n fẹ́ try láti develop níbi àwọn iṣẹ́ ilé ni wọ́n fi introduce the two inertial terms. So a dẹ̀ mọ iṣẹ́ tí inertial term tí ó máa ṣe níbi new algorithm. So ó máa jẹ́ ká ní strong convergence. So ó dẹ̀ máa jẹ́ kí so ó máa jẹ́ ká ní strong convergence. So nínú ibi àwọn iṣẹ́ tí a ṣe yẹn a try láti gẹ́gẹ́ bí nǹkan tá a máa ń fojú sùn níbi iṣẹ́ wa, a máa ń try láti wá boundedness níbi iṣẹ́, a dẹ̀ máa find the solution set. So lẹ́yìn ìgbà yẹn a máa wá nǹkan tá à ń pè ní strong convergence. Wọ́n dẹ̀ tún try níbi iṣẹ́ yìí láti fún wa ní numerical example. So ó yẹ kí àwọn nǹkan tí a try láti ṣe níbi iṣẹ́ yìí nìyẹn. So àfi tí a bá ní àwọn nǹkan míì tí ọ̀gá bá tún fẹ́ ká mẹ́nu bà sá.
So well, mi ò ní sọ pé èèyàn kan try nìyí, but máa sọ pé èèyàn kan try, and ta ló try? Dr. Aduke. So bí mi ṣe rí nìyẹn o, máa sọ fún yín o. So now ẹ wá wò báwo lèmi ó ṣe present tọ́lọ́ tèmi. Ẹ jẹ́ ká wò bí mi ṣe fẹ́ present tọ́lọ́ tèmi. The same thing tẹ́ present yẹn náà. Let me see. Let me present one. Ṣebí Ọlọ́run ti stop àbí?
Bẹ́ẹ̀ni.
Okay. Kọ̀sí tí n bá ní pé kí n bá múlẹ̀ kọ̀ọ̀kan pé nǹkan tí mo rí níbi presentation ni rè, nǹkan tí mo rí níbi presentation rè, it might not mo lè má lè catch up from what I was saying because I wasn't taking notes. Now, èmi mo fẹ́ review paper and say bẹ́ẹ̀ ṣe review. Look at what I'm going to do. First, nǹkan tó kàn mí láwọn nǹkan tí mo kọ paper yẹn, ó ní pé mo fẹ́ wo nǹkan tó sọ ń pa ẹ̀. And for every paper, ẹ máa rí nǹkan tó ń point sí nǹkan tó ṣe nínú ẹ̀. And that thing is what you call the abstract. That's the very first thing. So from there, you see whether what has been done is interesting or not. Ìyẹn aláwọ̀kọ́ number one yẹn. So now you go there. Now let me read that to you. Only in this work, we introduce two inertial type algorithms for solving relational inequality problems. So n tó kọ́kọ́ wà mẹ́rin pé nínú n tó fẹ́ ṣe ní pípa yẹn pé wọ́n fẹ́ fún wa ní method méjì. Then kí náà fi method yẹn ṣe, wọ́n fi solve relational inequality problem. Wọ́n tún wá jẹ́ kó yé wa pé kò ń ṣe relational inequality problem fún nǹkan kan o, but a relational inequality problem that is associated with a monotone and Lipschitz continuous mapping. You can see operator yẹn gbọ́dọ̀ wà monotone, number one, that's one condition. And the second condition is that what the operator has to be Lipschitz. That's another condition. Then nínú framework wo wọ́n kàn sí pé nínú Hilbert space. Because why have I said that? At a soft moving for our way, there are several frameworks, whether linear or non-linear. Frameworks like the norm spaces of the Euclidean space, the Hilbert space, the Banach space, which I already said Banach space. Now you can have there be four geometries. Then the non-linear spaces of the Hadamard spaces, the Cat0, Cat K, Cat1, and then the Hadamard manifold. Okay, so at that first sentence, ó ti cover nǹkan tó ń ṣe nínú paper. Sentence aláwọ̀kọ́ to cover nǹkan tó ń ṣe nínú paper. Wọ́n kàn elaborate more nínú the following sentence. So the first algorithm requires the computation of only one projection onto the physical set per iteration, while the second algorithm needs the computation of only one projection onto our space, and prior knowledge of the Lipschitz constant of the monotone mapping is not required, improving the strong convergence theorems for the two algorithms. First theorem, only require computation of one projection onto the physical set per iteration. So let's get x1 projection correlate, let's get x2 projection correlate, let's get x3 projection correlate. Then the second algorithm also need projection onto our space when you start it in here. And prior knowledge. And prior knowledge of the Lipschitz constant of the monotone mapping is not required. Ṣé mo pé operator yẹn ní monotone and Lipschitz, but wọ́n wá padà sọ fún wọn pé àti ẹ̀ ní ìdí láti evaluate Lipschitz constant yẹn. So this is what the paper intends. Once under some mild assumptions, I will prove strong convergence for the proposed algorithm, which means pé method méjèèjì tó give me ó jẹ́ strong convergence method méjèèjì. Wọ́n dẹ̀ sọ fún wa pé kí ni o, àwọn lo àwọn fún wa ní numerical experiments. That's the review of the article. So whatever they've done there, that's the review. What you're looking for now is an inertial algorithm. In terms one benyo, inertial or two inertial algorithms, in terms 1 year. To jẹ́ wípé projection kan péré ló need, ló ń lò. And lo Lipschitz constant. Now, to put it into context, I'll take our back on the methods that have been used to solve the same problem. So there are so many things, like this hasn't started with the Goldstein method, which is the gradient projected method, but glad we've mentioned that in the class. It starts with the gradient projected method, not with this. So this is an extra gradient. Extra gradient being that for each iteration, you have to execute A1, A2, MAG. They're going to execute A, so that's why it's called extra. This A is the gradient coming from the method that was used to solve the Picard method that was used to solve the minimization problem, where gradient of the converse lower semi-continuous operator is required. So from that, they coined the name gradient, and here being two gradients makes it an extra gradient. Now, apart from this projection onto feasible sets, to pose difficulty when the structure of this set is not simple. To convex set complex, getting the projection will pose a very, very great difficulty. And now, think of now doing that thing twice. To get x2, okay, to get x1, not to find x0 in C. Now, to get x1, for instance, you have to calculate y1, y0, you have to get y0 and get x1. So let's get y0, there's a projection and there's an evaluation of A. Now to get x1 itself, okay, let's get x0, y0 rather. Let me try to do that from here. This is the method, x0 in C. X0 is known, I'm x0. Now we compute yn to be equal to PC of xn minus lambda and axn. Then xn plus 1 equals PC of xn minus lambda n ayn. At x0, this is the initial point. Let's get x1, I need y0. Let's get x1, you need, this is going to be y0, because x1 will be when n is equal to 0, right?
Yes.
Let's get so that means x1, you are going to need y0. So, and y0 will be equal to PC of x0 minus lambda naught ay0, and x1 now will now be, as get the y0, so x1 will now be PC of x1 minus lambda 1, right? y0. Anybody? Can't get y0 again. PC A. Láti now get the sequence will be x0, x1, x2, like that. So let's get the x1, I need y0. Let's get the x2, I will need y1. Let's get x3, I will need the y2, like that. So for each x1, x2, if I get any lattice projection 1, evaluation A1, projection again, evaluation. So you're doing 2 projections and 2 evaluations on the operator A. So in here, on the far, we're going, is there a way of reducing this projection and we still get a convergence of the method? On the lead C method, sensor et al. Àti method SENG. You can also call it the The same method, we're going to focus on that because we're going to focus on paper here. So I'm going to write that because that's the focus of the paper. And what did they do? That's exactly what I was expecting. Apart from reading the abstract, then you come up with what they have done. So the Senc extragradient method itself is this way. PC xn minus lambda n axn, for instance, and xn plus 1 is, don't forget you need an initial point. So xn plus 1 equals yn minus lambda
n into
into
bracket
a
yn
minus.
minus
Is it AYN or AXN? Ìwọ ló yẹ kó kọ́kọ́ wà ní méjèèjì. With a minus or with a plus.
AYN minus AXN, no, correct.
Look at the minus or the plus.
Minus,
that's the
minus,
difference.
minus.
The minus is YN
Minus,
first. Okay.
Minus, yeah.
Yeah, so this is the Senc extragradient method, which is also called the forward backward
method.
Forward method. Forward backward forward method. So that's another name for it. Now, this is the Senc extragradient method. So it is clear that there's only one projection, right? And for each iteration, there are two evaluations of the operator A. That's why you see them still call it extragradient. That's why this is called Senc
extragradient method.
Extragradient method. This is extragradient not there. So no execution evaluation A comes twice. Now come to the paper. They said they want to do the same thing, the same method, but in this case now they are inertial types. So what I've written now is this only 5. So, but if you notice this 5 here, if you're saying this 5, lambda lele yabi.
Yes, sir.
Lambda lele is a constant. But what I've written here, sorry, what's that? What I've written here is a sequence. So in Yego that's an improvement on whatever they have written there. So, but in your colleague who called that former one, you need to one paper, the same paper, because you can't, because of just ordinary that constant, Latin copy paper me or something, unless you have not seen that somebody has written the same thing before. So, but in essence, that's what we're going to. Here, this step length, they said, depends on the Lipschitz constant of the operator A. Okay? Now, they now said somebody has done the same thing. Now, what is known, or what was discussed before or prior, is that this will not give a strong convergence. It's still weak, just like the previous method. It's not, at least it's okay here. So, but to make the method strong convergence, you can either add the Harpan step or you add the viscosity step. And sometimes they add the Ogazu. And I said Ogazu also involves projection. That's another extra projection. After having 2 projections, you have 1 projection. You add another projection, you're killing the algorithm. So you have this, that they've managed to reduce the projection to 1 using the Senc method. Now, to make it strong convergence, they've added the viscosity step. If you look at this viscosity step now, it is a convex combination of f of xn, f being contraction, and zn, which is the what? Which is the Senc step. Look at the zn. Eric, with zn here on the Senc step y. With the plus here is xn that's coming first. That shouldn't pose any problem here. If it is xn that's coming first, you see minus times minus will give you what? Has to be plus here. If you want xn to come first, that's what I was asking, which one is coming first. So, but if it is negative, then it's AYN that's coming first. So that's how the method is defined. Shane, get me?
Yes, sir.
Okay. Back to where the paper is. So now, viscosity method, or it include viscosity. It is the same thing, inspired by this Seng extragradient method and the viscosity method. Now, what have they done? Instead of having the step length to depend or be dependent on the operator F, they've changed. It was they started with an operator A. So for me, I always like people to be consistent. So if you're using A for an operator, and in the definition of the problem itself, they have used A. So I'd rather have an A all through for the problem than changing it here. So I would have preferred that they have A here, but do not be confused. The moment it's written this way, PC of xn minus clinical, you know that something variational inequality is coming. So the room just structure it, just know that variational equality is coming. So whether the operator is F or operator is G or operator is A, operator is whatever it is, the moment it looks this way, then it's VIP. Now, the lambda n here is not dependent on the Lipschitz constant of this F. They have updated it in this way. This is how to calculate the lambda n now. So this is one improvement again to the method by Seng itself, the original Seng method. It's an improvement because one, it's no more lambda, it's now lambda n, and that lambda n does not depend on the condition of the operator in terms of Lipschitz. Now, the same thing was done here in algorithm 1.2. But what have they done in 1.2 is that they have added another step, which is the inertial step. Anytime you see something like this, they call this inertia. So they have added inertia. Step 1 is inertia here, and yn, just like the other one, is still what yn should be. So they've replaced, you see, it was previously, I want to write that. So it was previously yn, okay, yeah, the previous one would not let it. So this is the same method. Now it's now starting with xn. So this form method starts with wn equals xn plus alpha n into xn plus xn minus 1. Okay, so instead of having yn to be equal to p of xn now, yn is now pc of wn minus lambda awn, lambda n awn. So see the difference. And then xn plus 1 rather will be equal to yn minus lambda n. Ah.
A of yn.
Ọmọdé yẹn ti ń kọ nǹkan sí ojú screen yìí o. Àbí? Gbọ́dọ̀ mi náà mọ ọlọ́gbìn.
Ọ̀dọ́ yín ni.
Okay, so lambda n. Ló ṣẹlẹ̀. Kò yé mi mọ́ o. Ó ti dàrú o. So, nǹkan tí mo try láti constant is just to replace this xn here by yn now.
By
so,
wn.
So by wn rather. So lambda n into, I don't know what's going on. Lambda n, so I'm going to change it. So that's exactly what has occurred to that. As a change, can you see? And if you look at it again, their lambda here, I want to support it. One should depend on Lipschitz constant here. One should depend on Lipschitz constant. So now the method they introduced in this paper is a combination of this algorithm 1.1 and algorithm 1.2. Algorithm 1.1 has step size. Algorithm 1.2 has inertia. So now let's now go back. Let's now go to the introduced method. You see, it started with the inertia, PC, the gradient step, then what is this? The Seng method, right? And the viscosity step with the step size. Every combination méjèèjì.
Yes, sir.
So whatever you're going to prove, then you're going to take it from those two. This step always is the same thing from all the three, from all the two, the previous two. Step you could change. What you should do is download the papers. Our paper, then see how they have worked out this xn plus 1. You are going to see that there's no difference. Go and look at how they've computed this yn, the same thing. The only thing is, xn straight ni, xn wn feni. Whatever is done to that yn there, where they have gotten xn, here will be bearing wn. So, and then we're not going to be, it's not going, I'm going to download it to show us. I'm actually will know. So we compare with what they've done here. Now, most important thing here, these ones are common to papers, because they've already cited it, so really MABAL everywhere. So, and this, to show that xn is bounded, anybody that has done anything with the SENG method will proceed exactly the way this guy has proceeded here. So I want to download one of those papers and compare. So, but now, after comparing, showing you that the next thing for you, I'm going to start it, is to now go and work them out. Work them out, because it's not all steps that they have taken that you're going to find in the article. So if you're trying to, there are some times that you need to do some maneuver. If you don't understand what has been done, it might be difficult for you, most especially if you want to present it. If you want to present it, it might be difficult. Not present in a conference or somewhere, like if conference present fellow me, okay, invitation, where you come up and stop or something. Now, if you don't know it yourself, so it will be difficult. So what you do is just go over it step by step. Like here, they've said by definition of Zn and using lemma 2.2. Then you go to 2.2. Kini lemma 2.2 kilo 1. Then which of lemma 2.2? In case sometimes the conclusion of those lemmas can be many, can be 3, 4, 5. So which of that has been used? So that you have to find that out. So let me go back to what I said I want to do. Download one of the papers and we see. Think one is tongue. I don't know the number. 30 something below your question. Yeah, this is it. So maybe we must share screen, have
Yes, sir.
Yeah, what is that?
34.
34, yeah. Méjèèjì náà ló wà lẹ́gbẹ̀ẹ́ ara wọn, yeah. So 34 and 35. 34. What I'm put 34. Èwo ló ní Nasha ní méjèèjì yẹn náà? I think it's the second one, right? Second one. Eléyìí tí ó ní Nasha mo fẹ́ lò. Eléyìí ò ní Nasha àti. And I'm trying to copy. Okay. So Delisha. Okay. Má bínú. Okay, now let's look at the main results now. This is the algorithm again. It's yn, pcxn minus lambda n, f of xn. You see what do you notice here? Fún xn plus 1, they've used the sequence what? Alpha n, right? Aha. But ibi tá a ti ń bọ̀, kí la rí ńbẹ̀? Kí náà pè fún wa? Wọ́n pè ní beta n. So nígbà tó state ẹ nínú preliminary ẹ. method yìí là lọ ibi tí eléyìí gangan làwọn èèyàn tá à ń bọ̀ ní ṣe rí pé okay yeah it's still alpha n wọ́n copy exactly bó ṣe wà mẹ́rin ní alpha n. So, but this alpha n, whatever condition this alpha n satisfies, is the same condition that this guy, the one for tongue, the same condition, no, satisfy beta n because it's still the same viscosity. So this condition here, every condition lim of beta n goes to 0 as n increases and the sequence is non-summable. That is, the sum is infinity. Non-summable. So if it is finite, the answer is summable. So this is not summable because it goes to infinity. So this condition here is the same condition that the alpha n here has to satisfy. And let's see if that is true. Alpha n here in that paper, should download and send. So alpha n, what is the condition of the alpha n? So it's not stated here. They will state it in the second place. You see, look at the condition. 33. So this condition has to be satisfied for every viscosity. So you have to take note of that. Now, I said whatever has been done to that. Now let's go. So they started this Zn minus u, the viscosity part. Zn minus u. Yn minus this is stated n minus u all squared. So now let's go back to my guys. So the Zn minus u2. So instead of u, they have called, they picked a point P. All right. So the same way, yn minus lambda n this guy, the first thing that comes in this is yn minus p squared. So in that case, you must have yn minus u squared as well. Where is it here? Yeah, you see yn minus u squared. Then this guy, this second expression is also the second expression that you're seeing here. But here, instead of it being wn here, xn because it is xn that you have there. So that's exactly what you need to do. Let's just open. Now, Eric owns it state lemma to low. But I'm going to state lemma and by. I'm going to state lemma to low. So that's why you have to find out what did they do to get this thing. So, and that this guy stated it here. On stated here. I'm using lemma 2.2. So you go and check what lemma 2.2 is. So what is lemma 2.2? How many conclusions lemma? 4. Then you're now going to ask yourself, which of these has been used? So now what I can see is that I saw the addition of two things and gives me 2 squares and an inner product. So, and an inner product, see where that is. Here, addition of 2 squares and an inner product. So which means it is one of 3 or 4. You can know 3 or 4, no, do one. Is it 4? No, there's no 4. You can't even, yeah, in fact, so they will use only 3.
Do you feel it?
Only 3, because only 3, you need 2 non-square. Yeah. So now, how did they use it? That's another thing that you have to find out. Now, I'll find out that this was what they used. Then, how did they use it? So that's the next thing. So I'm going to do one for you, and then you are going to go and find out the rest yourself. Go through how it has been done. So, so I'm going to start that first part. And one very, very important, which is always this addition and subtraction that we used to do. Completing the square method. Tama introduced dummy.
Yes, sir.
So you're completing the square method, for instance. Let's say you want to do x squared plus ax. What do? You have to add and subtract the square of half the coefficient of a. So this is like saying x squared plus ax plus a over 2 squared minus a over 2 squared. You can see that a over 2 squared minus a is still saying like, it's like saying you have added what? 0. So that's exactly what you are going to see most times in these things that we're doing. You have to do so many additions and subtractions. Let's expand some of those things. So let's see that method itself. Zn, which is yn, for instance, minus lambda n into AYN minus AXN. And we have said they use xn plus x plus y squared equals x squared plus 2 into x comma y plus y squared. This is the normal expansion x plus y. Is that not? By normal expansion x plus y squared, the normal thing. Ben, Abi?
Yes, sir.
So this binomial is except the norm, exactly. So this is x squared plus 2xy, yeah, plus y squared. So just that it's now in a space where this is the norm, and this is the inner product. The product, this product will be inner product in the new line. Now let's now consider that. Let's say we have picked a point. Let's like just said, we pick a point in the solution set. So Zn minus p squared will be equal to, you write Zn as it is, Yn minus lambda n into a Yn minus a xn minus p, right?
Yeah.
All squared. So I can write this again as Yn minus p, then minus lambda n into Ayn minus AXN. Do you notice something here? Níbi tí tẹ́ bá rántí, níbi tí ó ní convex, níbi convexity, let's say alpha NU plus 1 minus alpha NV, for instance. Tí mo bá yọ P kan kúrò ńbẹ̀, next step mi, U eléyìí, méjèèjì máa ní P, àbí? Exactly, méjèèjì máa jọ ní P, but níbi eléyìí, Yn nìkan ló ní P, side yìí ò ní P, because this is not a convex combination. Ṣé nǹkan tí mo sọ ṣe get nǹkan tí mo sọ ṣá?
Yes.
Dr. Aluko, ṣe get it, àbí?
Yes, mo get it.
So now there is a square here. Now I want to apply, this is the lemma I want to apply now. Because I'm applying. So now this, I treat this as A, and I treat this as plus B. Abi, X and Y. Don't let me say A and B now. X and Y now. So my X is Y minus B, and my Y is what? Minus lambda n. Exactly. So like that. So which means I'm going to now have Yn minus B squared, then plus, right? 2 into Yn minus B, comma, minus lambda n into Ayn minus AXN, right?
Yes, sir.
Then I close the inner product, then plus, I'm going to square this guy square. So imagine
Lambda n
minus lambda n squared minus lambda n into Ayn minus AXN.
No.
Squared, right?
Good. Yeah.
Norm Lily, this is norm. So now I can write this guy now as Yn minus P squared minus this plus times minus L. Mo lè gbé lambda n yẹn jáde is a constant. So minus lambda n, minus 2 lambda n into Yn minus P, comma Ayn AXN. So clear? Minus lambda n here, which 1 multiply plus 2 to 1 that no should be minus 2 lambda n. So Yn minus P, then this guy remains. Then lambda n 2 is a constant. Square inside the norm, I can bring it out to half plus lambda n squared into Ayn minus AXN squared. So when you get the first step, so clear?
Yes, sir.
Oh.
So when she gets to first step here on here. Now, if you now look at that first step again, if you look at that first step now, but you get first step in it. Now, step to tell you something has happened. So, but exactly, they've done an addition and a subtraction here because Teba will first skinny Yn minus 3 square because in by more. But ele second time ye, or she remain, or not ele. Third time ye, or not she remain. Abi?
Yes, sir.
So which means they have worked on this first term here. They have worked on this first term here. So what did they do there? They've added and subtracted. You see what they had? Xn. They've added and subtracted xn. So let me see. Let me show you how that is done. So if I add yn and xn, what does that mean? So I want to add yn and xn to this guy. So I'm going to have equals yn minus xn
Plus xn
plus xn minus p all squared. So the same thing, tí mo fi get the same thing. Now I can treat this as x now and y, x plus y. It gives me x plus y again, have it? So
Yes,
which means I'm going to now have yn. This thing has started this rubbish. So, but where I'm going to, if you understand where I'm going to, once you say addition and subtraction, xn and xn here, if you square it, just like so we are going to get that step that follows. So, sorry, we're going to get this thing. Oh no, open
Sorry,
up, see? Yes?
Sorry, sir.
Okay.
Okay. Èmi ṣe bí wọ́n lo triangular inequalities ní line yẹn.
But this is triangular inequality in Berara. That's one of those things that I was supposed to correct. In Kajola mentioned, there's nothing triangular inequality at all. Single triangular inequality there.
Okay.
It's just an addition and subtraction without the use of that lemma. So they have applied that lemma twice. Lemma 2.2 same. That lemma 2.2 as these guys have stated. This lemma. Lemma 2.23. So they've applied it two times already, man. No column the first step you back then way. Then that's if you get to step to totally then after that, so I'm going to stop it there, Lenny. Now that is how to start working on your sync method. Anywhere the same steps, but I want you to get used to it yourself. Know how those steps have been applied, whatever they have done, know it. So, and this again, it's the same thing that you're going to find there. But there's something I mentioned again. The same thing. That's how you're going to find it in those papers. Most especially if they are all used this guy. And we really look at the conclusion of the bandedness. This is the conclusion. Now let's go and look at the one for this other guy. I wanted to Kinshe Nasha. But only look at it. The only difference is that that other one has a plus n. Look it, the one where only plus n. So that's the difference. The same thing, less than maximum of this guy, comma, this guy. Only maximum of that guy, comma. This one, M1, it has come as a result of the inertia that was used. M1 as a result of the inertia. So, and if you see any people that has used inertia and this guy, you must see it this way. That way, that's all. So that, and the next thing they show, here, like it's just a dummy proof. Proof that's why they're proving this lemma. Assume that Wn and Yn are sequences generated by that, such that their difference as n goes big is 0. Then tó bá yẹ pé WNK yìí convert sí point kan nínú kíní ẹ̀, so point yẹn wà ní solution set yẹn. That's what it means. Tó bá yẹ pé Z naught yẹn lọ ó wà nínú H o, tó bá tí kíní ẹ̀ bá convert weekly sí point kan bí, the moment a bá ti rí tí kíní ìṣẹ̀lẹ̀ yẹ pé Z naught yẹn ó wà nínú solution of variation inequality yẹn, and that Wn minus Yn is clear. Only nǹkan tó wà bí ẹ máa rí yẹn from only when Wn equals Yn. What does that mean? If Wn equals Yn, kí lẹ̀ rí mẹ́? Eripo conform pẹ̀lú this called the fixed point formulation of the variation inequality.
Inequalities, yeah.
Yeah. Kí ni mo sọ ń bẹ̀ yẹn? Àlọ́ tí mo ń pa ń bẹ̀ ni pé kí ló ń ṣe kíní ìbáyìí nù? Ṣé mo tún change kíní lé ní ìbáyìí? Kò ń ṣe kíní tí mo ń lò tẹ́lẹ̀ lélẹ̀ o. I'm using Wacom tablet today. Yeah, computer for the Wacom tablet. Ṣé mo pé nǹkan tí kíní ẹ̀ sọ ni pé tí limit
Àwọn Wapcom yẹn máa ń ṣe ẹ lọ ra Samsung tablet.
ẹ wá ti fún mi ní òun ara o.
Ẹ kówó jáde, ẹ túkùn lọ́rùn o.
So ẹ mọ̀ pé nǹkan tó ń sọ mẹ́rin pé wn minus yn goes to 0 àbí?
Now,
Ẹ sọ pé if the limit of this guy goes to 0 as n goes to
N tends to
infinity
infinity.
and then wn converges weakly to a point, let's say P in H, then P is in the solution set of the VIP. Yeah, let's say C, comma A. Now, how do we know that? Wn minus yn equals tends to 0 means Wn equals what? Yn. And what is Yn itself? Yn is PC of Wn minus lambda n
A of
A
W.
Wn. So if Yn is Wn, what do you see? This is now Wn equals PC of Wn minus lambda A W.
A of
Setting
Y.
to arrive at the solution. I better get mine. So I put the fixed point formulation of the kidney is that when X is this guy.
Yeah.
So I get nǹkan tí mo try láti tàfà sí wáyé.
Okay.
Yeah. So the solution, whatever ti ní nǹkan tó jọ mọ́ tó rí báyìí, you have arrived at the solution, and that is what you're getting here. When Wn and Yn are the same, that is when Wn goes to and Wn minus Yn to bá fi lè lọ sí 0, you have arrived at the solution. That's why you see on state ìkànnì àwọn condition kìíní ẹ̀ pé if xn equals yn, then stop. You're going to see that here. If xn equals y, then stop. You've already arrived at the solution. So you mind?
Yeah.
So mi pé láti lè get a solution variational inequality wa, I need the key limit yn minus xn kó lọ sí 0. So yé báyìí. Níbi títélé, láti get solution set títélé, láti get solution ni, I need limit kí ni o? Yn minus wn. That's why you're seeing, they say if yn equals wn. Mo rò pé yé?
Yes, sir.
So, but they've just assumed those things first. Wọ́n máa padà establish wọn. Assume these are generated such that. So they assume this, and then wọ́n wá sọ pé if this is another assumption. So, but they will establish those things later. So, but they have proved it. Instead of repeating it again in the proof, it's already made as a separate separate result. Let's see if this one also did the same thing, or they did their different separately. First, they showed boundedness. When boundedness now showed, then Kinnon law, the next result is one. So the same thing, I will not say the same thing. Their next result is to make such assumptions. In fact, FL is sọ pé bóyá paper àwọn bọ̀bọ̀ yìí ń làwọn the other one yẹn náà dàkọ. FL sọ bẹ́ẹ̀, àbí? Ó tẹ̀léra wọn tààrà ni.
Same approach.
Exactly. Same approach. So same approach, same thing, there's no difference. So that's what you need to learn how they have achieved it. And but here I think there's something we call the case 1, case 2 approach. That's what these guys have used. Case 1, where you first assume the sequence is monotone, and a case where the sequence is not monotone. So we'll not be case 1, case 2, but I don't think that's exactly what these guys did in their own. Let me see. To show their own strong convergence, àwọn ò lo case 1, case 2. Àwọn ò lo. So they used another approach. So those are another things. Tebaka, kini teaching here, there is a point I mentioned something like that. We àwọn kan lo case 1, case 2, àwọn kan ò lo case 1, case 2. So there's somewhere there to mention rule from here. So what you should be on the lookout for is what you have to be on the lookout for. So that is where we're going to end it tonight. So if you've got any question for me, you can proceed to ask.
One question.
Okay.
I can share screen, Major. I can share screen, sir. Okay.
àwa tí a mọ̀ bóyá orúkọ wa bá rí orúkọ wa ẹ dákun báwo la ṣe máa bá orúkọ wa bá rí lẹ́yìn dákun ẹ bá jú ìlà àjọ bá ṣe fẹ́ mú bá orúkọ wa bá rí nísìnyí àwọn ìjọ dákun.
Hello, sir.
Yes, I'm with you.
Okay. So from here, sir, I know that this from the monotonicity condition, this tends to 0 because balance so eléyìí di 0, sir.
It will also the 0.
Eléyìí from the monotonicity condition T A of yn minus p, comma A of yn minus ap, comma greater than or equal to 0.
Exactly.
So, yeah. So báwo lè yọ síwájú di 0, sir?
Báwo ni ẹ ṣe di 0? Kí ni
Yes, sir.
definition of rational inequality? Go back to the definition of rational inequality.
Okay. What's the right, sir? What's the gate, sir?
Tell me what's the question. Is there another question?
Hello.
Yes, sir. Hello, sir.
Yeah. Simple question ni mo kàn fẹ́ clarification náà ni mo fẹ́. Níbi tá a ti sọ pé a lo numerical simulation yẹn, àwọn comment kan wà níbi bẹ̀rẹ̀. It's very simple tí mo kàn fẹ́ wo àwọn comment yẹn.
Ó yá wá gbé lọ síbi kíní.
Níbo ni, sir?
Numerical experiment, chapter 4.
Section 4.
Okay. Níbo níbẹ̀?
Àti débẹ̀. Àti ẹ máa lọ, ẹ ṣe máa lọ. No. Ìbẹ̀rẹ̀ section 4, section 4. Well, the statement is just the writer sọ pé I use my personal CP.
Okay. Yeah.
I use my personal CP, 8 GB, kankan. Why tí wọ́n fi lóru statement báyẹn mi?
Well, ṣe mọ̀ pé oníwàhálà ni reviewer mi. Most of them kò ṣe pé wọ́n máa ń ṣe kíní ẹ̀, wọ́n kàn wá béèrè láti wò okay, because variation wà láàárín àwọn systems ẹ̀ síra wọn, and you don't expect them to have the same performance. Again, tí mo bá ya nǹkan lórí tí mo bá ṣe simulation, tẹ́ bá rántí pé Dr. Àyàndá ṣe mọ Àyàndá ṣá. Àyàndá máa ń wá sí WestV látọ̀dọ̀ wa láti wá lo system àwọn èèyàn kan fún simulation. Nǹkan tó máa ṣe in bíi 2 hours ní WestV gbà yẹn, system tó ń lò lọ́dọ̀ wa gbà yẹn lè lo ọjọ́ méjì. So lára reason tó ṣe máa ń state àwọn property system téèyàn lò nìyẹn.
Okay. All right, thank you.
So if there's no more question.
Yes, sir. Gbogbo àwọn capture M tán ló yí báyìí. Mo rí pé wọ́n change M1, M2, M3 yẹn, mi understand it, sir. Wọ́n tún lo M4 náà, so here they use M1 here. So
in the definition
ìgbà tó yá wọ́n lo
definition M1, yeah, that's the thing. In the definition of M1, yeah. So go back to W minus P. So that's where the first M1 comes on here. So that's where the M1 comes. So O band. Also, now look at that thing. Wait. Also, from the condition that alpha n over beta n, O converges 0. Since the O converges 0, kini were banded here. Less than M1, M2, kini often band and kakani. So to balance M1, kini less than, kini less than, kini less than. So often band and number of money. So that's what it means. I'll become a band sequence.
Okay, sir.
So you got some clear, sir.
Oh, yeah, sir.
So now M2, we already the same thing. We open it.
Yeah, they use M4, yeah.
ìyẹn díẹ̀díẹ̀ wàá rí ibi tán ti wọ M4 kankan dédé fò sí M4 they have set this M4 but check it one by one níbi bẹ̀ yẹn the same thing lad lemma 3.6 check the proof conclusion ló kọ́kọ́ rí M4 yẹn that's the conclusion that's 18 it comes in the conclusion but
Yes,
now
sir.
how did they establish it so we'll prove yẹn that's how you're going to see it.
Okay, M4 is greater than 0.
So I need to just join
This
kí ni mo
from
sọ kí ni mo sọ sẹ́yìn look at the proof ṣé n tó mú ẹ ṣé o ti show proof báyìí look at the
okay.
proof and see how they arrived at the M4 mo sọ pé wọ́n fi M4 yẹ band nǹkan tó ń wò sí ibo lẹ́ M4 ti ban anything nínú nǹkan tó wà nínú statement of the proof nínú hypothesis yẹn does that show that M4 bans anything now check the proof and see what I've said.
Okay, sir.
Take it down máa gbé lọlẹ̀ díẹ̀díẹ̀ nínú proof yẹn to see where the M4 comes kí ló kọ́kọ́ rí mẹ́rin did you see M2 or not?
M2.
So what does that M2 do? Wọ́n fi band kí ni wọ́n fi band wọ́n ti fi band the kí lorúkọ ẹ̀ bẹ́ẹ̀ yẹn gbogbo 2 into Sn minus x star multiply by f of x star minus x star tó wà ní bracket in the previous step yẹn.
Okay.
Previous step you look at the previous step wo previous step yẹn expression mélòó ló wà ń bẹ̀ expression mẹ́ta that's the first one second one ni beta n multiply gbogbo nǹkan yẹn third one ni 1 minus beta n into zn minus x star and if you check the last one wà rí pé less than or equal to 1 bẹ̀ then gbogbo ohun tí beta n multiply ní second to the last step yẹn wọ́n ti fi m2 replace yẹn.
Okay.
So mi pé kíní tó wà ní bracket yẹn ó wà less than or equal to m2 of m2 band gbogbo nǹkan yẹn.
Okay, sir. Okay, sir.
Ṣé ẹ̀yin òkú get nǹkan tí mo sọ yẹn ṣá? So the same thing go through wàá rí kó tó kan m4 pẹ̀lú rí bọ́ sí m4 there is m2 that's m3 again ìyẹn náà tó ti band nǹkan kan mẹ́rin what does it band you can find it out yourself.
Oh, yes, sir. I'll see you.
So we stop there.
All right.
Èèyàn mi.
So ẹ ṣeun gan sir kí ni ká ṣe ní next.
Ẹ calculate àwọn kìíní yẹn so a máa mú pépà mi wá again tàbí pé ká tún ṣe further ẹ̀yin náà try láti wò ó bọ́n ṣe àwọn calculations yẹn ṣe get.
Okay.
So if there's anything bẹ́ẹ̀ pé nígbà tí ẹ ṣe lọ ẹ̀ríkà ibì kan mi ò get nǹkan náà ṣe bí ibi ìgbìmọ̀ yẹn láti máa gbé láti bẹ̀rẹ̀.
Okay. ẹ ṣe gan jazakumullahu khair.
Mi ẹ ṣe gan yẹn.
Kẹ mọ́ faralẹ̀ o.
Dókítà Àlùkò ti padà wọlé.
Rábọ̀ tí wọ́n ti wọlé padà.
Sọ́gẹ̀tì nǹkan tá a la máa ṣe báyìí.
Bẹ́ẹ̀ máa sọ fún ọ Dr. Àlùkò.
Yes.
Ṣe gẹ́tì ẹni tí wọ́n láṣẹ ní next Sunday sir.
Kíní mo wà offline níbi 3 minutes mi get ẹ̀.
Okay, wọ́n ní àwọn result yẹn ìrìn ní náà ni ká try láti prove fúnra wa délẹ̀.
Okay. Ká lè ní details understanding.
Wọ́n ní ká sọ̀rọ̀ ẹ̀.
So now tẹ́ bá ti solve so tẹ́ bá ti ní issue àbí ibi tẹ́ bá ti get them we now come and present it together àbí we work on it together so máa ṣe ni.
Yeah, but I must say that I'm gaining a lot color go by sign lesson.
Amen.
Kẹ mọ́ faralẹ̀ o.
Ẹ ṣe gan yẹn sá.
All right.
Ó dára sí.